Hello. We got an idea of the divide and conquer algorithm when we looked at the sample problem of identifying a defective coin. Before we look at other problems and algorithms that can solve them using divide and conquer, let us try to generalize the idea of a divide and conquer algorithm, and let's write down the generic template for a divide and conquer algorithm. So as we saw in the case of the defective coin problem, the idea of divide and conquer is if we are given a problem P of size n, and for convenience let's say n is a power of 2, n is 2 to the power of k, what we do is in the algorithm D and C, as the textbook calls it, divide and conquer, given a problem P, we do two things. First, we see if n is small, right? What does it mean for n to be small? That really depends on the problem. For some problems, size 1 may be small. For some other problems, size 2 may be small. Size 16 may be small. But depending on the problem, we decide what size problem is a small problem. And if it is a small problem, we don't apply divide and conquer. We simply solve it directly. For example, we use a brute force algorithm to solve it. Right? So in the case of the defective coins, if the size is 1, there is only one coin, we don't need to do any divide and conquer. We know that is the defective coin and the problem is solved. The second part of a divide and conquer algorithm is if the problem is not small, else we divide the problem P into, let's say, two subproblems, P1 and P2. Usually they are of equal sizes. So they will be of size n by 2 or 2 to the power of k minus 1. In general, we may not always divide a problem into two subproblems. We may divide it into three subproblems or some other number of subproblems, right? But the most typical cases are when we divide the problem into two or three subproblems of equal sizes. Then we solve those subproblems. How do we solve those subproblems? We solve them recursively, or we call or invoke the same algorithm D and C on the subproblem P1, and we invoke the same D and C algorithm on the subproblem P2. So what will happen there? If we call it on P1, we check to see if P1 is small enough. If not, we divide that into two more subproblems and call them recursively and so on. So this part is the recursive call that happens in divide and conquer. Having solved P1 and P2, we need to combine the solutions to the subproblems P1 and P2 to arrive at the overall solution for divide and conquer. So the generic algorithm is check to see if the problem is small. If it is so, solve it directly or using a brute force method. If it is not small, divide it into subproblems, solve those subproblems recursively by calling the same D and C algorithm, and then combine the solutions to the subproblems to obtain the solution for the overall problem. This is the general method of divide and conquer. So when you are given a problem P, we divide it into two subproblems, P1 and P2. So if P was of size n equals 2 power k, P1 and P2 will be of size n by 2 equals 2 power k minus 1. P1 may get divided further into P3 and P4. P2 may get divided further into P5 and P6, and all of these will be of size n by 4 or 2 power 2k minus 2. Now if P3 was not small enough, it may get divided into P7 and P8 and so on, where you will get 8 subproblems of size n by 8 or 2 power k minus 3. So when will this stop? These recursive calls give you a tree of recursive calls, and this stops when the problems become of a small size, let's say size 1, right? In that case, we don't need to divide them anymore, and we simply solve those problems. Right? The interesting thing to note in this recursive tree is the height of the tree. What is the height of this tree, or how many levels are there in this tree? You will notice that each time we do this, the size of the problem is getting reduced to half the original size. So here it was 2 power k, 2 power k minus 1. Finally, these are of size 2 power 0. right? So the height of this tree is k. This is very important when we analyze the complexity of divide and conquer algorithms. How do we get the solution to P? You take the solution for P7 and the solution for P8, combine them to get the solution for P3. Combine that with the solution for P4, you get the solution for P1. Similarly, combine solutions for P5 and P6 to get the solution for P2, and finally combine the solutions for P1 and P2 to get the solution for the original problem P. So divide and conquer is typically implemented recursively, which results in a tree of recursive calls as we saw here. So how do we analyze the complexity of this? How many times do we do any elementary operation such as comparison or some other operation depending on the algorithm? If we write that as a function t of n, where n is the size of the original problem P, right? If I divide it into two parts, it is nothing but the complexity of solving problem P1 and the complexity of solving subproblem P2. P1 and P2 were of size n by 2, but there is an additional cost involved in combining those solutions, and let's say that is some function f of n. So the typical recurrence relation or the analysis that we do is t of n is the cost of solving subproblem 1 plus the cost of solving subproblem 2 plus the cost of combining the two solutions. We are making an assumption here. The assumption is that the cost of dividing the problem into two subproblems is trivial or is a constant term. So we don't add one more term to include the cost of dividing problem P into P1 and P2. Right? So this is nothing but 2 times t n by 2 plus some function f of n, the cost of combining the two solutions. In general, if we divide it not into two parts but into some other number of parts, the recurrence relation for a divide and conquer algorithm takes the form, right, a times t n by b plus some function f of n. Right? So this is the typical recurrence relation for a divide and conquer algorithm. We will see how to solve such a recurrence relation. So in this case, we are dividing the problem into size n divided by b, and we get a such things. So it's a times t n by b plus f of n. Here again, we are assuming that each of the subproblems is of the same size. In general, divide and conquer can also divide a problem into subproblems of unequal sizes, but we will consider only this case of equal size subproblems. Right? So how do we solve these recurrence relations to obtain the complexity for a divide and conquer algorithm? There's a method known as the substitution method that we use to do this. For example, given this relation t of n equals 2t n by 2 plus n, so here we have divided the problem into two subproblems, each half the size of the original problem, and the cost of combining is f of n is just n, so it is linear in the size of the problem. I will apply the same formula to obtain the value of t of n by 2. So t of n by 2 is nothing but 2 times t of n by 2 by 2 plus n by 2. I have simply substituted n by 2 for n in the above formula. So this is nothing but 2t n by 4 plus n by 2. So let's take this, right, and substitute it in place of t of n by 2 there. What do we get? T of n is equal to 2 times 2t n by 4 plus n by 2 plus n. That is nothing but 4t n by 4, right? That's n plus 2n. How did I get that 2n? 2 times n by 2 is 1n. There was another n already. Now, how do I know what is t of n by 4? I substitute n by 4 in the original formula. I get the expansion for t of n by 4 and I plug this in here. So if you keep doing that, you will get things like 8t n by 8 plus 3n, right, and so on. When will this end? Right? This will end when we get, right, nt n by n plus how many n's will be there, right? So as this number increases, and for convenience we assume n is a power of k, 2 power k. After k steps, right, this number is 2 power 1, 2 power 2, 2 power 3, it will become 2 power k. So this will become n. In other words, if I continue that here, t of n becomes n t1 plus, what will be this number here, the question mark? That will be nothing but k. There will be k steps, right? So k times n. So we got two terms here, right? I no longer need to expand this. This problem is small. We can solve it in constant time. So the first term is n times some constant. So that is linear in n. The second term is n times k. K is not a constant, right? So essentially, we can ignore the first term because that is much smaller than the second term. That is some constant times n. This is something else times n. So what we get is log n times n, or what we normally write it as n log n. N times log n, by switching the two things. Why did we get log n? Because if n is 2 power k, then k is nothing but log n to the base 2. Right? So we can say that the algorithm is O n log n. This is very typical. You will see a lot of examples of algorithms in sorting and so on which have complexity n log n. And in each of these cases, the pattern to remember is we divide the problem into two subproblems of equal size, and then the cost of combining the solution is going to be the linear in the size of the problem, and that will result in n log n, and this is the method of substitution for solving recurrence relations. So the generalized divide and conquer algorithm, just to re-emphasize again, given a problem d and c of p, if n is small, solve it, for example using brute force. Otherwise divide it into some k subproblems, usually k is 2 or 3. Each will be of equal size n by b, so that n is b to the power of k, and solve the subproblems recursively by calling the same d and c algorithm, and then combine all the solutions. Right? So the general form of the recurrence relation is t of n is at n by b plus f of n. We already looked at the typical case where a is 2, b is 2, and f of n is n. And what did that give us? That gave us n log n. Right? Let's look at one more example. Here a is 1 and b is 2, and f of n is a constant. What does this mean? This means we throw away one of the subproblems. We consider only one subproblem. That's why a became 1. And there are still two subproblems, and they are still half the size of the original problem, n by b, where b is 2 is nothing but n by 2. Right? This is what happened in the case of the defective coin. We were able to eliminate half the number of coins. Right? So we were only left with half the number of coins. One subproblem need not be solved, only the other subproblem needs to be solved. And there was no cost for combining because we have already thrown away one subproblem. The cost of combining is a constant. If this happens, let's see what will be the recurrence relation. T of n is 1, or I will not write 1, t of n by 2 plus c. Right? So a is 1, b is 2, f of n is c. Applying the substitution method, this is nothing but, right, t of n by 4 plus c, which is nothing but t of n by 8 plus c plus c plus c. Right? And so on. Finally, we get t of n by n plus, how many c's will be there? Whenever we get n in the denominator, n is equal to 2 power k. So you will get k times c. We will have added c k times. So this is nothing but t of 1 plus k times a constant. T of 1 is a constant. It can be ignored. K is nothing but log n like before. So you get t of n is equal to some constant plus log n times a constant. Right? We ignore all the constant and say this is O log n. So this is another typical pattern. For example, in algorithms such as the defective coin and binary search and so on, we will get a recurrence relation where half the problem can be discarded, only one half is to be solved of the two subproblems, and the function for combining, the cost of combining the solutions is a constant. Then you get logarithmic complexity or log n. So let us look at a quiz question. Here we have a divide and conquer algorithm that divides a problem into 3 equal parts instead of 2, and each time it divides the problem, it's able to discard 2 of the 3. So only 1/3 of the problem needs to be considered. What is the complexity of this algorithm? For convenience, n is given to be a power of 3. N is 3 to the power of k. So is it theta of 3 power k or k times n or n log k? The correct answer is theta of k. How do we get that? T of n is equal to 1 times T of n by 3 plus some constant, which is nothing but T of n by 9 plus 2 times the constant, right? And so on. Finally, you will get T of n by n plus k times a constant. This division will happen k times because k is nothing but log n to the base 3. So the complexity is k times a constant or theta k. The correct answer is B, theta k. Thank you.